All right, let's see. So don't forget, you still got your lab number 5. The lab number 5 will be covered in the exam. It's going to be due next Tuesday midnight. That's kind of the latest that I can push forward. But if you can finish earlier, finish earlier. If you want to chat about the function tables that I spoke about briefly last time, feel free. I think you definitely want to get through that particular concept. That's the main learning outcome for lab number 5. And your written test number 2, I'm going to release the result later tomorrow. Okay, so you're going to see that. Still talk to me if you want to go over some questions we'll answer. And for your exam review sessions there, I believe the polling on E-class is going to close on Friday. But if you still want to indicate your availability, please do so. And then I will try to maybe confirm the time. Most likely, it will be over Zoom, so we can gather as many of you as possible. That'll be the point, really. All right, and at the end of today, maybe in the last 10 minutes or so, I'll also speak about your exam. Okay, you can also ask me questions, so I can also put up some PDF maybe later tomorrow. If there's anything I answer today, I can make it more written, so you can also review it before the exam. We'll talk about it in the last 10 minutes today. Okay. Any question about the course you want me to clarify? Okay. So let's do a recap over here quickly. All right, over here. So last time, basically, we review the idea about lifelock or divergence. So you want to be sure that whenever we talk about lifelock or divergence, it would be a scenario, again, like this. So let's take a look. So this will be a lifelock situation where in a concrete model, you basically got an infinite interleaving of the new events, and only about the new events over here, because correspondingly, you will have skip indefinitely in the abstract model. That's a lifelock, right? So if you look at the abstract transition, it's even more explicit. We have things like a busy loop. It's basically do nothing, right? Just get busy, consuming the resources of the computer without achieving anything useful. All right, so that's about your system and diverging. Make sure you understand the definition. You can look at the slides and look at the discussion we had earlier. And we introduced the idea about variance here. And just one thing to very emphasize here. Variant is not a cause of the lifelock or divergence. It's something else. Your model itself has the lifelock or divergence behavior because of maybe lack of guard or lack of invariance, things like that. And the variant is just one indicator to tell you, oh, there may be some warnings about the possibility of lifelock or divergence in your system, right? Just remember. And we talk about this plot over here, right? So based on the trace that we did earlier, we also try to plot over here. So there are several observations you want to remember. So number one, so as you get the O events in the trace, they might either strictly increase the variant value or they simply maintain the variant value. Either way, it can be either maintained or strictly increasing. And we got to be sure, as soon as we try to decline the value for the variance, it will be because of the interleaving of the new events. And we want to be sure the variance is such a measure that it never goes below 0. So this really tells you that the interleaving between the new events will be limited or finite. So we can never have divergence. Right? Just remember the observation. Yeah, question? Say it again, sorry? Exactly, yes. So you can say that. So we would say that if, just remember one of the variant proof obligation is the variant should always be a natural number. So in this case, yes, exactly. So if you go below 0 over here, you can keep going like this. Of course, you will go negative, potentially to negative like infinity, right? So definitely. All right, so these are the several observations you can review. Unfortunately, I couldn't really get a recording to be recovered, but I also give you guys the links about other videos. They cover the same material. Please review the notes, and then if there's certain stuff you want me to repeat, reach out to me, office hour, or we can talk about it again in the review session. Right, we can do that too. All right. All right, that's about the general trends about the plots. I think I really get this trends very understood. That can give you lots of good intuition when you look at the proof obligation. And when we look at the actual proof obligation for variance, we got two of them. One is the variant value should always be a natural number. Okay? You should never go below 0. Below 0, like what your classmate said, you might just suggest there's an infinite interleaving of events. And the second one here is to say whenever you're making a transition of the new events, you want to make sure it's you can see new event here. That's important. It should strictly decrease the variance. We want to make sure the number of interleaving of the new event should be bounded, right? So if you think about this is the pre-states of the new events, this is the post-states of the new events. If you go from pre-state to post-state, it should strictly decrease the variant value. That's why we said here, the V prime over here is strictly larger than, sorry, V prime here is strictly smaller than V, right? Just don't get the relation opposite. So it might be something worth putting on your data sheets, which I'll speak a little bit more about today. Okay. Any question about the two proof obligation here for the variance? And of course, you have to also make sure you understand how this particular guy here for the go, because that one does involve some post-state value for the transition by the new events. You want to make sure you know how to derive it. But the way we derive it is very similar to how we did it for invariant preservation. Okay, so it should be nothing too difficult. And there was some exercise for you guys, and that one really corresponds to one of the slides I want to show to you, slide 80. So the correct variance for the system should be 2 times A plus B. That's where we derive the general trends from. And I want you guys to try A plus B as well. For example, if I simply give you in the exam some potential variance in the system, and then I'm going to ask you, based on this variant here, is it a good measure about the system for LifeLock? All right? But anyway, so give it a try. And the way you try it, you can look at the description here. You want to retrace the value of V using this particular event trace over here, and try to see if the general trend is still being followed, and try to see if the proof obligation can be actually discharged. All right? All right, important exercise for you. And then we also spoke about 3 new inference rules, which we're going to use today, right? So we got ORR, that simply say if you got disjunctive go over here, then because of the justification, like we got shunting, we got contrapositive, etc., right? So now in order to do it, well, you can look at the justification again. I may not dive into details again. So this, but intuitively, if you got a disjunctive go, you can simply move one of the disjunctive operand over here and put it as negative. I mean negated on the left-hand side. And then this one here, and L, if you got a hypothesis that's simply conjunction, that one there you can simply separate it by comma. All right? And we got another one called and R. That means the conjunction happens to the right of the turnstile. So this one tells you if you got a conjunctive go, you can split the original sequence into 2. So the way to interpret this would be to prove this one here, it would be sufficient to prove this one here and this one here as well. Both of them. Both are required. And we did a little bit of exercise over here about how we can split, right, the sequence, right? You can also review this one here from last time. I think that's basically where we were from last Thursday. Any questions from last time? If no, let's now move on. All right, so now I'm going to dive into a topic called relative deadlock freedom. So the new word here is relative. All right, and the slides, you can see the definition there. Let's take a look, and I'll guide you through a little bit. We're going to do a little bit of a planning for like an intuitive sketch before we look at a proof obligation. The slide number should be 81. Okay, so what we did so far relative to, well, what we did so far with respect to deadlock freedom is when we actually talk about M0, the initial model, we want to make sure the model itself does not deadlock, right? And that's what we can recall briefly. Right, the proof obligation name is called DLF. You can look it up, right? That'll be part of the study you have to do for the exam. And then we also talk about guard strengthening. All right, that's something you also want to review, especially when I talk about the proof obligation for relative deadlock freedom in the context of refinements. You might easily confuse about the guard strengthening proof obligation and the relative deadlock freedom. Of course, one thing you can do is maybe put both of them on the data sheets, but I would suggest also understand why they're a little bit different. Okay, we'll talk about it. All right, just don't forget, we already spoke about deadlock freedom for the initial model without the refinements. And we spoke about guard strengthening in the context of refinements for individual events. All right. What we need to say now would be something called relative deadlock freedom. Relative in the sense that when you have a refinement model there, it should be relatively deadlock free with respect to the abstract model. That's how you can think of it intuitively. All right. And that's a proof obligation. But before we look at that, let's now sketch something on the paper, right? Just make sure at least you get some intuition. All right, so let's now talk about some principles, right? And then once we talk about principles, we'll talk about relative deadlock freedom. And then at the same time, I will try to maybe sketch very quickly again the guard strengthening proof obligation so you can do the contrast at the same time. All right, several things. All right, let's now talk about principles. Okay, principle number one. Let's agree deadlock is a bad thing to have. You definitely don't want your system to really do nothing useful, right? Deadlock is bad. That means in the refinements, you should not really try to introduce deadlock scenario. Right? That's a consequence, right? It's bad. So the refinement should not introduce anything that's bad. Refinements should not introduce a deadlock scenario that is not existing in the abstract model. All right, the second point here is really important, right? So the refinement model here could be, in our case, M1, all right? And the abstract model here will be M0. And when you try to refine M1 from M0, you want to make sure there should not be a deadlock scenario that exists in M1, but that scenario would not deadlock in M0, conceptually. But we're going to see logically how we can formulate it in just a moment. Okay, let's now try to rewrite this slightly. Okay, just a little bit even more intuition. From point number 2, let's now be more precise about what's really unacceptable for a refinement model. It is unacceptable. All right. If there is a state S such that if you can find a witness where in S the abstract model does not deadlock, but the concrete model does deadlock, then that's bad. All right? Such that the abstract model does not deadlock in S, but the concrete model does deadlock in S. Right? It's really consistent with point number 2. I'm just trying to say that in a slightly different angle, right? Just want to give you more intuition. Right? It's unacceptable over here. And then we talk about concrete model over here. Let me use a highlighter. Okay, abstract model and also concrete model. All right, that's something to remember. All right, let's now look at the diagram here. This diagram here kind of represents what we want to prove. This diagram here represents what would be unacceptable. All right, let's now take a look. And then after these, we're going to look at, let's look at the proof obligation right away over here. So this DLF over here, when we formulate the DLF, is also for deadlock freedom. But when you formulate this proof obligation in the context of refinements, it really means relative deadlock freedom. Okay. So DLF over here, in our context, it really means relative deadlock freedom. Deadlock freedom in concrete model. All right. And of course, you can also revisit the formal definition, but I can tell you right away, so you don't need to go back for now. What we put as part of the hypotheses over here is the disjunction of the guards of all the abstract events. All right. So this would be the disjunction of all abstract guards. Abstract guards. And the consequence that we have over here, the goal, it will be the disjunction for all the concrete guards. So this part over here will be the disjunction of all concrete guards. Okay, so here is the concrete, right, versus abstract. And let's now contrast right away what the guard strengthening proof obligation would look like, right? Because it seems to be the opposite. All right, so if you recall about guard strengthening, which I'm going to put over here. So that one there, and of course that one is a GRD proof obligation, right? I'm just going to mention exactly what the proof obligation is, and then it will be up to you to go back to the intuition description about guard strengthening and revisit and compare what I say today about relative deadlock freedom. I'll leave that to you. But let's just recall the guard strengthening would look like something like we got some other hypothesis, and then we got here HI. Turnstile, GI. All right, and of course, this H over here is a concrete guard for some events. Of some events. And this G here, GI, is the abstract guard of that particular events. All right, you can see, seemingly, it's a little bit confusing. I got H here, I got H here, right? I got G here, I got G here. That could be the seemingly confusion. However, not quite. Let me point out to you something you want to think about when you review the notes, right? When we talk about the guard strengthening, we talk about individual events guard. So here we talk about a single events guard. And the concrete one should imply the abstract one. On the other hand, when we talk about here, it's not just a single event. It's about the disjunction of all the events together. And somehow, the logical relation should be flipped somehow. All right? But I would say rather than memorizing it, try to go back to the guard strengthening there, revisit the intuition about it, number one. Number two, I'm going to talk about intuition for this one here. Try to focus more on the intuition rather than being so confused about which one should put which, right? If you really forget about if you really forget about where to put which in the exam, recall the intuition. That might be the best way. All right, I'm going to leave the review for this one here for you. Okay, I'll leave that to you. And let's now talk about the intuition for this one here. And the intuition really follows through point number 2 here. We do not want the concrete model to introduce any bad behavior, basically. Okay? How can it introduce a bad behavior? Okay? So this one here is about the relative deadlock freedom provable. So this will be the scenario we want to prove. All right? Since we say the disjunction of all the abstract guard should entail the disjunction of all the concrete guard. So we can draw a circle like this, right? You can see this one here is corresponding to this. And turnstile is like a subset or implication. And this one here is like the bigger circle. We talk about this when we talk about weaker versus stronger predicates, right? You may want to see that too, all right? So there's few things I can assume you guys have already studied. So make sure you review. If you still got trouble, let me know. All right, so this one here, this part here can really be visualized into this diagram here. And what does this diagram really mean? Right? Let's talk about it. For example, if I take one state over here, okay, let's say here. What does this state really mean? Beg your pardon. Let me just turn it off. Good. Right, you can see this state here exists in both here and here. So this is a state where at least one guard in the abstract model holds. That means at least one event is enabled. Similarly, at least one event in the concrete world also is enabled. So this is an example state where neither of the model deadlock. All right, both models not deadlock, basically. Okay, so this one here is a state where both abstract and concrete models do not deadlock. Are we okay with this? Okay, again, you can see this particular state exists in the intersection of these two circles over here. That means this state here must satisfy both this and this. This condition here tells you at least one guard in the abstract world is enabled. And this one tells you at least one event in the concrete model is enabled. Right? So this is the state where both worlds actually does not deadlock. All right. So we want to make sure whenever we have a concrete model over here, we do not really introduce any bad behavior. So everything that's possible for the concrete world is also possible for the abstract world, no exception. All right, so that's one way to understand why this is the valid one. Okay. On the other hand, if you look at, let's say, a state from here, what does this state really mean? Right? Okay, anybody tell me in this state? Just like the way I said, this state here is the state where both the concrete and the abstract, both the concrete and the abstract do not deadlock. What about this state here? Anybody want to give it a try? It's okay to guess. Yeah, go ahead. The concrete can deadlock? Actually, no. I tell you why not. You can see this state here is within this disjunction here. So that means this is a state where the concrete does not deadlock. Okay, maybe that's what you meant to say. But be careful, in the exam, you got to say exactly what you meant, right? Okay, good. All right, so this state here, you can see that's within this circle here. That means the concrete model does not deadlock. But the abstract model, you can see this state here is not a member of this smaller circle. So that's where the abstract model does deadlock. Let's write it down first and understand that it may not be problematic. Okay, so this is a state where the concrete model does not deadlock, but the abstract model deadlock. And this one here is not a bad thing. To put it the simplest way, this one tells you in the abstract model there is certain scenario where we might deadlock, but now in the in the abstract model there is certain scenario it might deadlock. But in the same scenario for the concrete model, we resolve it. We don't deadlock anymore. We are not introducing anything bad. We are doing something good in the refinement. Let me say that again. This state here is not a bad thing because it represents a state where for the abstract model, that state will deadlock because it's outside the disjunction for all the guards. But in the concrete model here, it somehow resolve the deadlock. So this state here does not really deadlock for the concrete model. So we are doing something good for the refinement. All right, that's one thing to think about it. All right, so what we have just said here, this really represents very like an intuitive sketch about why it should be the abstract implies the concrete. Question? Why it is good? Sure. First of all, you can see this state here, right? Over here. This one is outside the circle over here. Okay, the fact that this state here is outside this circle here tells you that's a state where none of the guards for the abstract model will be enabled. Because this circle here tells you the condition where this circle here tells you the condition where at least one guard in the abstract model will be enabled. Outside that tells you none of the guards will be enabled. So this point tells you this is where the abstract model may deadlock. Number one. Number two, the same state here is within this disjunction of the concrete guards. That's within it, so that means this is the same states will not deadlock in the concrete model. So we basically, for the same states, we go from deadlock in the abstract model into not deadlock in the concrete model. So we have to resolve something for the deadlock from the abstract world. So we are resolving something. We're not creating something problematic. Okay, think about it. Remember we said deadlock is bad, but resolving deadlock is not bad. Okay, that's why I talk about the principle first. All right, so to really finish off this intuition here, let's see something that's not good. All right, let's see. So let's say we don't really have this kind of a subset relationship between the two, like what's said in the proof obligation. Let's say we have some general. Let's say they somehow intersect, but they're not exactly subset of one another. So why is this one bad? All right. You guys can think about it. I'm going to point out to you. Look at this particular states. Okay. If you look at this state over here, what does that mean? All right. This is a state where, all right, number one, the abstract model, and then the concrete model. I'm gonna leave some blanks over here, and then of course I'm gonna give you the answer, but I want you guys to think about, all right? So here, the state for the abstract model, we're gonna say whether we're deadlock or not. And also for this concrete model, we're also gonna figure out, sorry, there's a bad color here. Here, all right? If I choose this particular witness states, for this particular witness states, I want you to tell me, does this state represent a state where the abstract model is gonna deadlock or not? The same states, is it gonna represent a state where the concrete model is gonna deadlock or not? And for those of you who are still not exactly sure about this thing here, this will be the disjunction of all the abstract guard. This will be the disjunction for all the concrete guards. Okay, 1 and 2. You might be wrong today, but that's okay. Just that's why I want you to struggle through a little bit. It's not easy at first. Yeah, go ahead. Why don't you say number 1? This is a state where the abstract model deadlock or not. Yes or no? Abstract model will not deadlock because. Are you able to explain why? Why not? Yeah, you're basically right, but just you got to formulate answer a little bit better, right, for the exam, right? You're quite right, because this is a member of the set of satisfying states for this particular predicates. This predicate here is the disjunction of all the abstract guards. So this is a state where the abstract model does not deadlock. All right, very good. You're getting there. Okay, so now does not. Okay, and then the second one will be very obvious. You can see this state here is outside the region of this circle here. This circle tells you all the states where the concrete model does not deadlock. But because this state here is outside that region, so that state tells you that's the state where the concrete model deadlock. All right? So for the same states, we basically go from the abstract model where it does not deadlock into the concrete model where it does deadlock. We are introducing something bad, as I said in point number 2. All right? So when you review, you want to really convince yourself, number 1, about the principles. Number 2, you want to look at the legitimate situation. Number 3, about the invalid situation where you have a witness states that shows you we have introduced something bad, namely deadlock in the concrete model. And number 4, look at the proof obligation, which tells you exactly this. And final thing, also review guard strengthening. All right, several things. Any question? All right, so think about it. All right, you guys do have some time, before the exam. So struggle through the concept a bit. I think that's important. Okay. All right, so that will be the proof obligation that we have to discharge. All right, and the next page will be, let's now try to formulate them quickly. Okay, which is not difficult. All right, so this guy here is exactly this guy here. All right, Deadlock Freedom. Relative Deadlock Freedom, since now we're in the context of refinement model. So we're going to get a disjunction of all the abstract guard that should entail the disjunction of all the concrete guards. We're going to look at that in a moment. And then we got axiom invariants and concrete invariants. That's what we're going to get, right? All right, so let's now do that quickly, right? There's only one proof obligation, luckily. So you only got one proof obligation sequence for the relative Deadlock Freedom, right? Only one. Because you got to put disjunction of all the events together, not individual events. All right, so we're going to get, so this part here is pretty much standard, but I'll still do it. So this one here is going to be axiom and abstract and concrete invariance. So we got D natural number, D larger than 0, and also abstract invariance, N is a natural number, and also N less than or equal to D. And also we got concrete invariance. A is a natural number, B is a natural number, C is a natural number. And also A plus B plus C equals N. And also A equals 0 or C equals 0. Okay, quickly. This part here is the axiom. And this part over here is the abstract invariance. And this part over here is a concrete invariance. Okay? And we are missing this part over here. So that will be the disjunction of all the abstract guards. Oh, by the way, so when we talk about the guards over here, you should really include ML out, ML in, and also IL in, IL out. All right, you should do that. Okay, so for the abstract guards over here, we're only going to include basically ML out here, ML in over here, right? These two. Let me just change this one here because I do want to reserve the green for something else. Okay. Sorry for the waits. There we go. Okay, so turnstile over here. Before the turnstile, before that. So we're going to get the disjunction of all the abstract guard, which would be disjunction of this and this. So n less than d or n larger than 0. So all these are the hypotheses, right? Especially this one here correspond to here. So this is the condition where the abstract model does not deadlock. And what about here? This one here is going to be the disjunction of all the concrete guards, including the new and old events, which is going to be this, 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 and this. So it's going to be this one here, this one here, this one here, and this one here. 4 of them. Okay, let's write them out quickly. It's going to be a new line in the guards will be as if we have a conjunction, right? That's something we said earlier. So for the first one, for ML out, it's going to be A plus B less than D, and C equals 0. You can put a parenthesis, right, over here, just to be more explicit. And the second one there is C larger than 0, over here. And then A larger than 0. And then over here, B larger than 0 and A equals 0. And we're going to put disjunction between them. Or. All right, so that's the relative deadlock freedom. The proof obligation itself is pretty straightforward to put because it does not even involve any post states, only the pre-states, right? You can see there's no prime, there's no before after predicates for us to consider. But I think the more important stuff, if I may go back quickly, is to understand the intuition about the relative deadlock freedom, which I spend more time on. Right? So that's something you want to focus on for sure. All right, there we go. All right, any question? And the next step, of course, is to prove it. All right, the proof is already on the slides, and I will leave that as exercise for you guys. And the proof this time is going to make use of the inference rule that we spoke about last Thursday, especially these 3. 1, 2, and 3 here, some of them. So when you look at the iPad notes, which I'm going to release maybe tomorrow, the way we're going to do the proof is rather complicated proof. You start with this sequence here, which is what I formulated over here, right? You start with this. And we split that into 2 parts. Part number 1, you're going to actually start from this and then go with some steps until you can reach some intermediate sequence over here. So this is some intermediate one you want to get to start with part 2. And then from part number 2, you can try to discharge this sequence from then on. Let's finish that. So 2 parts. Again, you want to go from here to try to see how you can go from here to this part over here. And then from this part here, which will be the starting point of part 2, you can discharge it. Of course, if you want to charge everything at one go, that's not a problem too. I just want to make your life a little bit easier when you practice. And for part 1, you're going to need these 3. And for part 2, you're going to need these inference rules. Of course, also try to practice without any hints, or have all the inference rule in front of you to see which one to use. Okay, good. Yeah, the solution is on the slides. If you can finish another, let's say, alternative proof tree that's kind of different from the solution, feel free to show it to me. I can verify for you. With you, how about that? Okay. Just come to my office hour, and then we can go over them together. So this will be the last bits about refinement number 1, M1. Okay, and let's do a very quick summary, and then we'll take a short break. All right. So what we have done, we have seen concrete model number 1, M1. And don't forget, we also got M0 with respect to it. So that's why we say this is abstract, this is concrete, right? I put both models side by side over here. And the correctness criteria that we have proved and formulated for the refinement is here. Okay, let's take a look very quickly. We got something called guard strengthening. That tells us for the O events, for example, here, for example, ML out over here, the guards should really imply the corresponding abstract guard. That's just one example, right? We're going to do this for all the O events. And we got invariant establishment. That one there is not too weird. That's just about the inits, the same as before. That one, pretty straightforward. We also got invariant preservation. And the way we conducted the lecture was we kind of split into 2 parts. One part would be about invariant preservation for the old events, and also the invariants for the new events. But when you think about it, when you review for the exam, they should be thought about as one unit, right? So when you think about invariant preservation, it should be for all the events. ML out, ML in, the old events, IL in, IL out, they should all preserve the invariance. And we talk about convergence, meaning that your system does not lifelock, right? And the way to measure that is by using a measure called variance. Right? Of course, we got a story about how you can observe the trends, and also got the 2 proof obligation. And let me remind you very quickly. So here we got the 2 proof obligations, which is the var and also the net. And you should really look up to see what they are. And the one we just talked about today was something called relative deadlock freedom. That's the final one. So relative deadlock freedom. And that one there is basically about combining the guards for the abstract and compare them with the guards for all the concrete events, including the old and the new. Right? That's something we did also just a few minutes ago. All right, so that's about refinements. And before we take a break, let's see what we're going to do after the break. So after the break, we're going to introduce the second refinements. Okay, that'll be the last refinement we're going to do for the bridge controller. So in the second refinements, we're going to talk about what would be the new variables that we're going to introduce to add more concreteness to the model. And then just remember all the correctness criteria that we spoke about for M1, they will apply to M2 as well after the break. All right, that's something we'll do after the break. Okay, why don't I pause the recording now, and then why don't we take attendance right away? All right, so before the break, we finish our first refinements, all right, over here. And we are just going to use maybe about 20 minutes or so to talk about the second refinements. And we'll hopefully can finish some introductory part for the second refinements, and we'll do the more core part on Thursday. And hopefully we can finish the most part on Thursday, and then for next Tuesday, it will be the last class. We'll see what we can do, right? We'll see. Just don't forget, when we talk about the refinements, so these are the correctness criteria for us to really show and prove. Okay, just don't forget. Let's go over a little bit slides about the second refinements to see, well, even before I talk about the refinement, you want to think about, I should really expect to see more variables, right, to see more concreteness into the model. But let's see exactly the variables we're going to introduce. Okay, so that's before the break. Everything has been covered. And that's the proof I spoke about before the break. It's pretty long one, so you guys can practice and check your answer. It's okay to be actually different from this proof over here as long as you apply all the inference rules correctly. So show me your proof if you are having any doubts. Yeah. Okay, so that's a summary right before the break. Okay, good. All right, so now we talk about M2. So that's our new concrete model, M2. So while before the break, we said M1 was a concrete one. Now M1 has become the abstract one. All right, just remember. Okay, we're going to add more concreteness into the M2. even more concrete perception of the bridge controller, right? So you just recall very briefly, from M0 to M1, we added a notion about a bridge, also one way. But now, and in the M2, we got to add in the concept for traffic light, all right? That's something we're going to see. So this is just an analogy. So we kind of zoom in to the island a little even closer. We can see even more scenario, right, from above the air. So we're going to introduce two variables here, all right? So that's something you guys will have to get familiar with. Let me see here. Okay, good. So two variables here. One is called MLTL. The other one is called ILTL. So MLTL stands for mainland traffic lights. So TL basically for traffic lights. And then we got another traffic light put in place at the other end of the bridge, ILTL. IL stands for island, TL traffic lights. All right, we got two traffic lights. So these are the two variables we have introduced to M2. Okay. And all the correctness criteria that we set earlier before the break, they should be somehow reformulated in a different context and also redischarged. In the subsequent lecture, we are not going to talk about all the correctness criteria. We're going to talk about the more important ones. Okay. So let's now take a quick look. So we are basically addressing more about the E descriptions over here. Let's review them quickly. So environment constraint number one, the system should be equipped with two traffic lights. That's exactly what we're doing. And each light should have two colors, green and red. No yellow, no ambient light, only red and green, no intermediate light, all right, for simplicity. So we got green and red, and we got two traffic lights, right? That's exactly what we base our added concreteness on, environment constraint number one. And environment constraint number two, the traffic light control the entrance to the bridge at both ends of it, meaning that we assume that if, for example, this light here is red, no car should really go from the mainland to the bridge, meaning that ML out should not really occur when the traffic light is red. Similarly, if the ILTL traffic light is actually red, we also assume that IL out should not also occur. There should be no car trying to go from island onto the bridge if the traffic light here is red, right? Similar, okay? And environmental constraint number three, the cars are not supposed to pass on the red light, so we assume everybody obeys the rule. If we don't have this assumption here, our model will be very hard to really get right. Let's make that assumption. So it's important for you to realize environment constraint number two and number three, without these constraints, without these assumptions, it will be very hard to predict the model. Because even if the red light is actually on, there might still be cars passing through the bridge and incrementing the counter. That means everything we try to prove is no use, something like that. All right, so these are the relevant constraints that we're trying to address for this new refinements, M2. And then I put M0, M1, M2 in the same page, side by side. Let's now review again what we have been so far, right? We started with M0 over here, the most abstract model, where the island and the bridge are the same compound. There's no distinction. And then when we get to M1, which is more concrete relatively with respect to M0, that one there, we try to zoom in a little bit closer. So we do have the bridge over here, and the bridge is assumed to be one way. So that's why we got A here, B here, and C here. We also introduced the ILN and also IL out. All right. And in this latest refinement here, we try to add two more things. So we got here and here. So these are the two traffic lights that we're adding. We still got A, B, and C that we're going to somehow manipulate in our model. We'll see. But just remember, we got traffic lights, and we still got a one-way bridge, and we still got the flow measure that we used to have in the M1. And it would be worth mentioning some terms over here. Okay. Notice one thing here. When we went from M0 to M1, when we go from M0 to M1, if you recall, the only abstract variable we have was called n. Somehow n was not really referred to in any of the event actions or guards. They are not really accessible. All right. The abstract variable n is not accessible by n1. Okay, that's important. Maybe you didn't really realize it, but that's true. All right. The only place where you can see some n here in the M1 is in the invariant, the linking invariance. That's the only place, or safety invariance, not in the event, guards, or action. So when I say accessible, I really meant by event, action, and guards. Okay, that's what I really meant. And then when we now go from M1 to M2, things will change slightly, a little bit different. Okay. So when we go from, let's say, M1 to M2 over here, the abstract variables now is going to be the A, B, and C, right? A, B, and C. They are accessible, or you can say inherited to the refinement, if you think about inheritance analogy in Java. So here from from M1 to M2, the abstract variables A, B, and C are inherited. I'll put in quotes. It's not really like a formal term, but you can understand it that way. Inherited and accessible, as opposed to not accessible, right? And accessible by the concrete model, in this case, M2. Right? Notice that one is about accessible, the other one is not accessible. Notice the difference here. And there's a special term for this when the refinement model can actually get access to the abstract variables. It's called superposition. You'll see the term also in the slides. Right, so this particular scheme over here is called superposition. All right. Good. All right, any question here about this introduction? Okay, just don't forget, we got 2 traffic lights over here, and still, after what you can expect to see will be, we have to still prove the correctness of the refinements. Okay, let's just revisit them very quickly. All right. For example, invariants, establishments, and preservation. And also we got guard strengthening. And also we got relative Deadlock Freedom. And of course, we also got convergence, lifelock freedom. All right, so we got 1, 2, 3, 4, 5. Yeah, so we are only gonna discuss some of them in the lecture on Thursday and next Tuesday, but there might be some missing parts which we didn't really cover. Well, but you should really be able to do them as well. That's something we already did for M1. you should be able to do the same for M2. That's something I want to emphasize in the beginning. Okay. All right, any questions so far? Okay, I would say we go for another maybe 10 minutes or so, and then we can talk about the exam, just a little bit more. Okay. Let's now talk about what's really there in the model. Okay. Okay. Okay, we got, let's see. That's the environment constraint I just spoke about. And, all right, so the static part. We have a carrier set. Well, we have a set here called color. That's going to be color for the traffic lights. And we have two constants. We got red and we got green. And obviously, color should be defined as just a set of green and red. Okay? And then green is not equal to red. Axioms. Straightforward. Okay? And what about dynamic part? And the superposition I just mentioned in the previous page tells you that the concrete model M2 can access not only the concrete variables, like ILTL, MLTL, the traffic lights, but also can access the inherited abstract variables, A, B, and C. That's superposition. All right, so that's a diagram I just showed to you. I got A, B, and C, and the two traffic lights. So these are the state variables for us. All right, so now what we need to do is to look at two invariants over here, right? So you can see here, invariant 2 means M2. And then the 1, 2, 3, 4 over here are the indices for the invariants. We got 4 of them, right? The same convention as before. All right, let's now take a look. I think that these are rather straightforward, so I'll just give you the answer directly. But it's also important for you to see why they should be there. Right? Okay, we got here we got variables, right? You can see ABC, MLTL, ILTL, and we got these two. We say MLTL, the traffic light should be a color, either red or green. It will go from red to green or green to red. Only 2 possible states. Similarly for ILTL. Okay, and we got these 2 invariants to fill out. Okay, and so here are some hints over here. For this one here, we want to say if the cars are allowed to exit from the mainland, that would mean we got the cars being limited, and also there should be no crash possible. All right. So take a look at this informal statement here for a moment. And of course, it's very informal. But somehow we need to formulate it in logical sense, right? In logical operators. So for example, you can see means over here. And also, and. Well, this one I could have spelled it out. But that one also is a huge hint about what you can do. All right. So if the cars is really allowed to really exit from the mainland, so our assumption is the traffic light here cannot be red, must be green. Otherwise, car cannot really go out. They only go out if they follow traffic light. So for invariant 2, 3 here, we're going to have MLTL, which is referring to this traffic light here, equals green, implies. Right? You can see the means over here is corresponding to implies. Right? Implies 2 things. One would be the number of cars is limited, and also there's no crash. No crash is easier. If you want the car to really go this way here, you better make sure there's no car here. Right? That's something we spoke about earlier in M1. So C is equal to 0 should be something. So we're going to get C equals 0 should be part of it. That'll be the second part. No crash. What about limited cars? You want to make sure A plus B over here has not reached the maximum possible yet. Remember, the maximum is specified by the constant D. Right? That's something we did earlier. All right, so we're going to say A plus B strictly less than D. And then we're going to say N. So this will be the invariance. It's an implication where the MLTL, this traffic light here is green, means the car is limited, and also C is equal to 0, meaning that there's no car coming this way. Right? Any question about this? Some little exercise for you to think about. All right, I'll put it here. Start. Why not A plus B strictly, rather than strictly less than D, but less than or equal to D? Apparently, you can see here, I am including the possibility of equal. Okay, here is a question for you to think about. Why not? Exercise. Little hints for you. What you want to think about is, in order for this part of the invariant to be preserved, you want to think about if we really allowed Emma out or some car to really go into the bridge, how are these variables going to change? If you think about it, you will see that equal sign over here is not a safe edge case to include. That's my hints for you, right? Think about it. Okay, so that's about invariant 2-3. All right, so let's now talk about this one here. So this one here, we got similar pattern here. We still got means over here. Okay, and also end. So here, the antecedent is going to be being allowed to exit from the island. Being able to exit from the island, that means the car is going to see the traffic light here being green. All right, so that will be the antecedents, right? So for invariant 2-4, I'm going to put here, that one there is going to be ILTL. ILTL equals green. Implies two things. So one thing here and one thing here. The first thing here, there is some car in the island. Because if there's no car in the island, it's simply just empty. There's no car we can expect to go onto the bridge, right? So B should be larger than 0, for sure. And also no crash. That means A here should be 0, right? Hopefully that one's a bit more straightforward for you. So B larger than 0, and also A is equal to 0. So that's the second invariance. Of course, here we are taking some shortcut. I'm telling you the answer directly, so you will try to convince yourself they really make sense. In reality, if you really have to build this from scratch, you may have to come up with different versions of the invariant and try them out to see which one works better. But that's okay. All right, any questions so far? All right, if no, let's see. I think it might be good to maybe pause over here a little bit. Okay, I got about 10 minutes here as a promise. I'm going to talk about the exam. Okay, how about that? Let me pause the recording just to be safe, and then I'll re-record again. Okay, let's talk about the exam. Okay, so you can also get started early if you wish. Okay. All right, for the exam, well, you know the time and location, 7 p.m. to 10 p.m. Sorry, that's what the register office decided. So, but Sunday, December 15th. On the bright side, we got enough time, right, to really have you review, and then we can schedule some review sessions. That'll be the big stadium, you know, around the tennis center, right? You know where it is, pretty close to Bergeron Center. Coverage will be everything. Well, it will be materials and also the labs. You got to review everything I posted on the lecture site, and also your lab solution as well. That's what you should do. And you got to review specifically the slides and iPad notes that I posted on the lecture site. So the way I generate questions for the exam will be I will go over the slides and particularly what I discussed on the iPad notes. And I'll try to see if there's any point that's worth asking you guys for understanding. That's what I typically do. So what you will see is everything that appear on the exam paper should be something that we already covered. Okay, so that's the principle. The formats, I don't really want to commit to whether I'm going to have multiple choice questions, but I can expect mostly written. It's a paper test, mostly. There could be some explanation, justification. For example, I might give you, well, let's say for example, right, in the math review lecture, I might give you some set over there and ask you, is this a member of a partial function? For example, you're going to explain to me whether it's yes or no. Also similar like a justification. If I give you a model and simply ask you, is this model here Deadlock free? You're going to show it to me as well. You may have to formulate a proof obligation and then try to discharge it, something like that. And you may have to write some math expressions. So here, I would suggest you put down the rodent syntax that you're not very familiar with, the common ones on your data sheets if necessary. So I'll be very explicit about in the question, in the answer, should you actually put in the rodent ASCII syntax or math form? So when you review the slides, make sure you can distinguish well between either the ASCII versus math. ASCII versus math. You might be expected to do some calculation, and you might be expected to do some proofs. And for the inference rule, we may not give you any extra sheets, so make sure you put down the rule you need on your data sheets. Okay? Okay, what will be the restriction here? So you got some one-sided, mostly computer. You know what? Let me relax this slightly. This is the principle, right? I can tell you what would be unacceptable. I don't want the whole thing to be completely handwritten. I want you to start with computer type first to be more organized. And then if you want to add something more at the last minute by handwriting, it's okay. Okay? Should be computer typed in the first instance. And it is okay to add some handwritten info in the last minutes. That's okay. But it should be minimum. The minimum should be 10 PT. You cannot go smaller than that. Okay. The sketch paper I'll provide to you, so you don't need to bring your own. Okay. What's going to happen is I'm going to give you two booklets. One will be the exam question booklet. Okay. So I'll give you one will be the question booklet containing the questions only, and you got to make sure you return this booklet at the end of the exam. You cannot take it, right? Make sure put your names to the number and etc. If we don't receive the question booklet from you, we're not grade your exam. Please, okay? Make sure you return. So there will be a question booklet, and also there will be answer booklet as well. So in some ways, it's kind of feedback from the previous year students. They said that if the the question and answer separate, it's easier for you to flip the page for the question. So it's really for your convenience. Okay. So and also answer booklet. I think one should be enough, but we'll try to prepare some spare ones. If you really need a second one, that's fine. We can also give that to you. All right. So you can expect to get two booklets. And please make sure you got your physical photo ID. And because we are not going to allow you to put the mobile phone on the table, they're going to be stored on your back underneath the table. So please make sure you bring us physical ID. And if you want to bring any water, snack, no, not a problem if you need it. I know it's pretty late in the evening, so you might need some energy bar or something. You might. All right. Guys, ask me a question. I can answer about the exam. I haven't really finalized the question yet, but I'll try to see how much I can answer today. Yeah, go ahead. You got to put on your, yes. But, this is how I would suggest. I'll give you some example. If I were you, This is how I would do it. Give me one moment. But feel free to take my advice or ignore that. Doesn't matter. Okay. Let's say, for example, I would say, oh, by the way, I have already put all the inference rules on the lecture site. Everything's there. Okay. I would say on the sheets number 1. So that's the first set that we talk about here. You don't really have to put, for example, let's say ORR1. Maybe that one's simple enough. You don't really need to put the whole definition to occupy the space. Maybe all you got to do will be to put the name of the rule in the paper so that when you look at that, you know exactly what it means. On the other hand, when you look at ORL, maybe that's something you want to remind yourself exactly what it looks like. Maybe that's the thing you want to put in the actual sheets for definition. And for monotonicity, I don't think you really need to put a definition there. That one's also quite obvious, right? So you can decide. All right, so that's the inference rule. Yeah, so please make sure you put down the ones you need. Yeah. Yeah, you can put screenshot. That's not a problem. But of course, you got to make sure the screenshot is not too small size, right? Okay, no problem. Put screenshot. And as I said on Thursday, I don't mind if you guys collaborate on the data sheets before the exam. That's not a problem either. I will encourage you guys to do so. Actually, not a problem. Okay. The font size, exactly. You can put as dense as you like. There's no limits on the margin. How about that? That might help, right? Okay. When I put out the PDF tomorrow, I'll mention that there's no margin limits. Okay, but font size limits, yes. All right, any other question you want to ask me about the exam? All right, yes.
What would a question look like relating to the lab content?
Okay, it's let me try to answer that. Yeah, so the question was, how are the exam questions going to be related to the labs? Let's say, for example, let's say for lab number 2 and 3, which are about the celebrity problem. I might give you something very similar, maybe rather than celebrity. For example, what you guys did for programming test number 1, the registration problem. That one basically looks very much like a celebrity part of. I might give you a new problem there, and where I may just want you to put some invariants there. I might give you the English description and want you to put the invariants, something like that. Or maybe I put something that I said that should be the invariant, justify whether that's appropriate or not. Yeah. So you got to be very familiar with, don't just memorize the facts in the labs. I might give you just some different context, which will require the same complexity of the constraint to be put. Yeah. And for lab number 5, it's also important. You may be asked about tabular expressions. So please make sure you also do lab number 5. Question. Yeah, exactly. So in terms of whether you're going to write in the math form or the ASCII rodent, I'll be very explicit in the question itself. So again, similar. I would say I'm pretty sure for many of the operators in rodent, you know how to do them. But for those, it might be easy for you to forget. You put on the data sheets. Yeah. You don't need to. So basically, in the actual exam, if I really want you to maybe do something about M0 and 1, I would say now consider the following model. So I'll give you the details there. You don't really need to memorize the details of the model. You don't need to. For example, let's say this. I might give you, let's say, M1, M2 side by side as part of the exam question there. And now I say, now formulate the relative deadlock freedom proof obligation. In which case, you just have to know what to include. You don't need to remember the details of the model. Yeah. Good. Also, for proof obligation, you want to make sure. Sorry. Every time different music. Sorry, overtime. Okay, very quickly. So I would say for inference rule, you definitely want to include the ones you might be easy to forget for you, but also for the inference rule and also the syntax as well. So can you say that again? What you said earlier? The question. Yes, for the models, the short answer will be no, you don't need to memorize the invariants or something in the models. But of course, if there's certain invariant you believe has a very good pattern for you to refer to during the exam, you can put it down as well. Yeah. All right, guys, any other questions about the exam? Yeah, go ahead. Yeah.
So regarding the final test, do you think it's
If you really ask me, if I look at the exam individually, individual question, they're really, well, if you really ask me, right, I wouldn't say they're very hard, but I think because it's cumulative. So you guys have to study everything. So you might find that, it's actually something from here, so it can feel hard. So I would say, yeah. Okay. All right, so that's general information. I'll put up another PDF tomorrow. And then for tomorrow, if you got a question about lab number 5, it will be the last lab session for you to come. All right, see you on Thursday.